Thank you. So global quantum intelligence, it's the coming together of fact-based insight, quantum computing report and interference advisors. We follow the quantum tech sector globally, and we work with investors, with startups, with players in the sector. I'm gonna deviate from my script. Thanks for joining at the tail end of the second day of the conference. I'm gonna deviate from my script a little here because I want to try and work in some of the themes we've heard talked about at this conference. And also I'm gonna try and call out things that maybe haven't made it to this conference but have been interesting over the last few months. I want to start out by picking together this. It's a map of the global economy, and let's look at where some of the key use cases are for quantum. So the two that are flagship applications, cryptanalysis, quantum simulation for material science, quantum chemistry. We often talk about these because these are where we would typically say, well, there is an exponential advantage to be had by using quantum computers. And it's important to realize that these are really in fairly niche areas of the global economy. And it's interesting to see who talks about them, of course. We haven't had ANSI or GCHQ or NSA presenting it at this conference or any conference like this, but of course, this cryptanalysis application is something they care about deeply, and that's one of the reasons why that public funding will carry the quantum sector through to ultimately deliver these machines. Quantum simulation, now we heard a great presentation this morning from Bob England. Even though this is one of the great applications, the scale of machine, the large-scale fault-tolerant machines required to deliver applications like that are challenging. Some interesting about whether in material sciences the applications may be a little bit smaller. Some hope that we can get through applications in the NISQ period there. We also talk, of course, about machine learning and optimization. Optimization is a ubiquitous hard business problem. Machine learning, of course, is finding an incredible number of use cases across the board. But remember here, the quantum ideas we have are heuristics. We don't know the ideas we can implement now. We don't know exactly what advantage they may offer. We can't prove that, and that's not necessarily a problem. A competition between quantum and quantum-inspired and improved classical algorithms can still deliver business value. It's very interesting to hear the Q-Star presentation earlier that reminds us of what an emphasis this has been in the Japanese ecosystem. But if we're looking for a larger advantage in this period from this type of application, then you've really got to ask, what is the intuition that quantum is going to deliver some large value? And that's more evident in some presentations than others when we look across what the vendors talk about. And then, of course, because of that cryptanalysis threat, we face the challenge of how to protect our cryptography. And of course, for most users, the first solution will be maths-based post-quantum cryptography. But we were reminded this morning, of course, that for users with more aspiring security aspirations, there are new options coming available from quantum cryptography. And in Eleanor's presentation, she reminded us that it's also about much more than that. There's much more that these quantum networks can do in terms of advanced protocols and other things. And of course, not to forget quantum sensing, which is a very interesting area in its own right. So I want to press on and introduce our quantum computing stack that we use to analyze the sector. And of course, the notion of the tech stack has evolved. At the beginning of conventional computing, we had what would become software sitting on top of a variety of hardware platforms. And I'll go quickly here because this conference, we've already had a great discussion of how its HPC and the modern HPC stack is one of the great places that we'll see quantum fitting in. Now, I would call out here, one of the things that GQI is following carefully is the Ibm Serverless Initiative in the sector at the moment. IBM has been very influential so far in terms of its previous framework initiatives, whether that's OpenChasm, whether it's Qiskit. IBM Serverless it's going to be interesting to see what influence that has over the ecosystem and how it develops, how we'll think about computing in this heterogeneous environment. Let me a little bit more specifically about the quantum stack and how we analyze it before I get into to specifics. Of course, it's not just about the qubits in the quantum plane, though of course they're very important. It's also about the control plane, the signals that let us control those qubits. It's also about the control logic, in particular for calibration and for error suppression, optimal control of our qubits. It's also about an architecture, ultimately an architecture that's going to let us do error correction. It's about a framework, the frameworks that make it convenient to program these devices. It's about algorithms. And of course, as we've had pointed out to us, that's where the real magic happens. Quantum computers are slower than conventional machines, but the algorithms let us do things that we couldn't otherwise do. And of course, we want to form those into applications. Now, I'd love to talk more about algorithms, because there's been a lot of interesting, in some cases, challenges in algorithms, and in other cases, interesting program. But I don't have time today, and my focus is on the hardware. So I'm going to drill down into the hardware part of the stack now. So first of all, going to the bottom of the stack, this is the key area for us having usable NISQ devices. And one could talk about, and GQI respects the efforts to create more usable benchmarks, and benchmarks that it's easier for users to engage with. But sometimes when we talk, and too many times when we talk about benchmarks across the sector, it obfuscates the basic reality that the devices today they don't have high enough fidelity. Particularly, we need qubits which have longer coherence times, faster gates, and in particular, 2-qubit gate fidelity remains a key benchmark and a key problem for devices in the market today. Having 3 nines fidelity in a hero device isn't good enough. We need 3 nines fidelity or more across a device in simultaneous operation. And the current generation of devices are not delivering that. Now, one could go away and say, well, look, we've got various vendors and we've got trends of their fidelity over time. I think that type of chart can be misleading, because often what we see at the moment is vendors that are trying to get their simultaneous qubit fidelity back up to what has been demonstrated in a 2-qubit hero device. And the problem there is we're not going to go past that already not adequate performance without something different being done. And I'll come back to some of the new technology ideas later. But the first thing to talk about here is what are the ideas to help get this generation of devices over the line. And there's one that we think is very interesting in GQI, which is the IBM 100 by 100 challenge. What it's doing is this time it's trying to marry the big bird scale with little bird fidelity. And if IBM can do that, they're also going to add on aggressive parallelism and aggressive error mitigation to deliver a device that can do 100 qubits by 100 circuit depth in a day. Now, that isn't a slam dunk for any known application, but it does give us something that it's then very interesting to try to see what we can do with that. Now, I flag it particularly because I also view it as disruptive. Because the point is that error mitigation doesn't fit with the conventional algorithms that people are playing about with at the moment. And that's going to mean that if people are going to be able to take advantage of that capability, either the IBMs are living. It's interesting to see there are startups like Kedma has been represented at this conference that also are working on ideas in this area. New thinking about the algorithms that we put on top of that capability are required. Now, another idea to implement things with these devices that we've heard a lot about at this conference is analog mode, particularly on the neutral atom devices. And analog mode immediately has my interest as a scientific application. I think it's very easy to see how this is a very interesting thing to do to simulate exotic physics. To believe that it's going to work for commercial applications, we have to have an intuition that the noise isn't going to become a problem. These devices are no less noisy, but I have to believe that that noise isn't going to be a problem for my application. Now, that's easy for exotic physics, perhaps. But when we transfer it to other applications, we've got to be able to carry on that metaphor. Or we need to have interesting ideas about how we can work with part analog, part digital, introduce some error mitigation into that analog world. It's also interesting to see startups like Kipu that work in this area represented at this conference. Now let me move on beyond the NISC era. How do we then scale up to larger devices? So the first thing we have to worry about is the control plane. And the problem for our existing architectures is the control plane doesn't look easy. Superconducting circuit devices, when I put them in my fridge, if I want to introduce any control or multiplexing logic into the 20 millikelvin stage of the fridge, that's adding an active heat load. But even worse than the active heat load, just running wires down into my 20 millikelvin stage is introducing a passive heat burden into that stage, a very significant one. And it's not clear how easily you can scale around this. Interesting, ideas in the market, but it's a challenge. And people might, to give a sentiment, people might say, well, we'll put more control logic at the 4K stage. But you've got to remember that between 4K and 20 millikelvin, it's like comparing this room to a blast furnace next door. It's a massive difference. And so there's a massive heat load just by having connections to the 4K stage. Moving on to, say, trapped ions and neutral atoms. It's great that we work with lasers. Lasers have many great properties. But when we want to scale up our control plane, scaling integrated laser control is a major challenge. These are God's own qubits. But that also means they operate at God's own frequencies. And it's a nasty mix of frequencies that I have to do my optics to bring those lasers involved. And clearly there are ideas here, and we've had ideas hinted at in the presentations at this conference. But this is work that's yet to be demonstrated, that it can actually be done at the scales that we're talking about. And it needs to be done at wavelengths it's not so easy to work at. Photonic devices. Photonic has a tremendous influence overall across the quantum ecosystem. But the photonic quantum computing devices we see at the moment, they're not really integrated solutions. We're typically having to get the right properties from the right materials between sources, interferometers, detectors. We're having to work across multiple devices. We're having to couple on and off chips. And that's difficult. I need to be able to do that at a compatible set of wavelengths. I need to be able to do that within a tight loss budget. So again, there's challenges here. Let me press on. And sometimes people, they talk about, oh yeah, it's great. We can scale up to a relatively large module size. I can do 10,000 qubits maybe in my module. I can do maybe 1 million qubits in my module. But there's a hard fact that if you look at the error correction overheads, that's not really enough. Almost all roadmaps assume that when the scaling gets tough, we ultimately go modular and have interconnects to get the scale up. And interconnects are a problem. They're a particular problem in superconducting circuits when not much has been demonstrated at all at the moment because of the particular wavelengths we have to operate at. And even for technologies such as ion traps and neutral atoms, in reality, the interconnect demonstrations we have are not really fast enough, not really high fidelity enough, and haven't really improved significantly for a whole bunch of years now. So there's a challenge in getting interconnects that are operational to deliver these modular architectures. And one of the go-to solutions that you would naturally start to think about is that I'm going to use some type of optical cavity to enhance my interconnect coupling. But I have to do that and build these interconnect cavities without disturbing the fidelity of my underlying device, and that's a real challenge. And we'd also really, really like better error-correcting codes. Surface code has been great because it can be implemented with nearest neighbor connectivity. We think we can basically get over the error threshold for it. But in reality, with the error rates that we're seeking to target in these devices, we end up with massive overheads. further exacerbated by the need to use the magic state workaround to develop a full gate set. And it brings, I think people have heard Earl Campbell present yesterday about some of the challenges of decoding logic to work with these systems. And if nothing else, Earl's presentation should remind us there's a lot of complexity there in just making decoding work. So I want to talk a bit more about this scaling challenge with error correction and why we think it introduces for some disruption. I'll come back to that later. So this is that overall picture, and there's a lot of challenge on it to build these large-scale fault-tolerant devices. And there's a key takeaway that we wanted to show by sharing this chart, that it's not that the leading architectures at the moment are somehow so far ahead that there's no room for further innovation and startups in the sector. Because it's not that these challenges are unaddressable. Clearly, these teams have ideas to work on these. But there's space for other technologies to come and play catch-up. So in particular, it's interesting to look at what's happening in superconducting circuits. For a long time, the go-to strategy has been transmon and coupler as the basic architecture. It's interesting to see a whole series of new designs which go beyond that. They're post-transmon designs. Interesting to see where they're coming from. They're coming from China, coming from Japan, coming from Europe. Very interesting to see the NEC LHZ architecture, something that came out of, it's originally known as a coherent quantum annealing architecture, but more recently been demonstrated as being able to support a universal gate set. Interesting to see in trapped ions. The leading platforms, such as IonQ and Continuum, they use laser-driven gates on hyperfine qubits. And that makes the laser optical integration challenge that much harder. It's interesting to see a whole brace of startups in Europe, and basically their strategy is to not use laser-driven gates. It's to use global field microwave, near field microwave. Near field microwave has the interesting additional string to its bow that it potentially offers a route to a significantly higher gate fidelity. Photonic, it's been very interesting to see a brace of new materials. The architectures we've known about have been silicon on insulator, silicon nitride. There's issues about the loss in silicon and insulator. And one of the key challenges for those platforms is that they don't operate a good way to provide a fixture. They rely on thermo-optic switching, which is slow and not cryo-friendly. Interesting to see a brace of startups embracing different technologies. Turing Q, Yihan Quantum in China, looking at thin-film lithium niobate. Interesting to see Quix in Europe trying to add lithium niobate to the triplex platform. And perhaps most dramatically, PsiQuantum announcing a remarkable pivot where they've stood up a facility to add barium titanate on top of silicon wafers. And this is about adding electro-optic switching to that photonic tool set and letting you do a bunch of new things. Interesting to see also Candela and what they're doing with 3-5 compound semiconductor sources, which is potentially a much better way to do your sources photonic architectures. Neutral atoms, very interesting to see shuttling, and we saw Katira demonstrating that with a lovely illustration. Interesting to see initiatives, and we if the Australians were here, they would certainly be talking all about silicon spin, and I'm sure our Dutch colleagues would as well. If I press on, there's a bunch of interesting other innovations that cut across this. And those electro-optic materials that help photonic qubits, they potentially help all of these interconnect problems as well, because not only do they offer electro-optic switching, they also operate at different wavelengths, more convenient wavelength windows if we can work with them. Interest of time, I want to push on to another key point. Several of these technologies help us with the path to FTQC. Working with the surface code, we're committed to an architecture which ultimately requires millions of qubits. And that's where a lot of when we hear presentations which talk about the large machines needing millions and millions of qubits, it's based on assuming a build of a surface code architecture. Now, it's important to remember there are other strategies in town. If you can have a qubit platform that does a significantly higher rate of fidelities, that ratio Whereas with 3 nines fidelity, I might need 1600 to 1 physical to logical qubits. With 4 nines, it's potentially 160 to 1. There are startups that will tell you that's what they're going to be able to do. It's interesting to see Alice and Bob here with their cat qubits. Cat qubits potentially give us a very different error-correcting architecture with a lower overall overhead. It was very interesting to see recently Photonic Inc. talking more about their startup that's been in quite deep stealth. But at Boston, they were talking more about their architecture. They're the first startup to be openly targeting a high connectivity quantum LDPC code with a much lower overhead ratio. And if that can be stood up, if they can really deliver the architecture that supports that and really demonstrate how you add fault-tolerant computation on top, it potentially is a radically different overhead. Now I'm out of time. Eleni talked about this morning, the different paths to networks and different routes. There's a disagreement in the market about, are we going to see early broad quantum advantage? We're going to see a quantum winter. Is it going to be easy to build quantum computers, or is it going to be difficult? And they represent different views that affect valuations in the market. So thanks very much.